Hi, my name is Samuel Lee, and this is my Physics 2211 lab number 1, constant velocity. To begin, I will outline the purpose of this lab and the fundamental physics principles in this introduction. The purpose of this lab is to demonstrate the difference between the motion of an object with constant velocity in a computational model versus an observed model. This object not only has constant velocity, but is also moving in only one direction. The computational model we use is based on fundamental physics principles. Something like this would be important because what has been calculated can differ from what will occur in real life, which we see in the experiment in the observed model. Additionally, we will also see that the experiment showed a slight difference between these two models. The reason behind this will be discussed later in the report. To start with some of the fundamental physics principles, Newton's first law states that an object in motion or at rest that's not acted upon by some outside force will stay in motion or at rest. Essentially, the object has a tendency to resist changes in motion or rest. Newton's second law states that an object's acceleration is directly proportional to the net force acting on it, or it's inversely proportional to its mass. The equation below shows that, as you can see, the mass and acceleration are on both sides of on the same side of the equation. Lastly, constant velocity occurs when net force is equal to 0, and therefore, according to Newton's second law, the acceleration would also be 0. This means that the velocity will remain constant, as there's no force, as the net force is 0, to act on the object, and Newton's first law states that it will remain with the constant velocity because it will stay in motion. So next up, I'll talk about the observational model. Tracker was used to investigate and plot the motion of the object. The system was denoted to be the moving object, or more specifically, the cap of the marker. The surroundings would be everything else around the system, including the table, like the normal force from the table, gravity, friction, the push from the hand. The marker was chosen because the marker's cylindrical shape would allow it to roll with less friction in comparison to other objects. And then we also used a short clip to maintain the constant velocity after the first push force is applied, so theoretically it would stay with constant velocity for a brief moment after. And then also we have our computational model here. Glow script was used to calculate the movement of the object. The ball's initial velocity and the initial position you can see on the slides there. The initial position was taken from tracker based on where the axes were set. In order to keep things constant between the computational model and the observed data, we chose to use this. The ball's initial velocity was calculated by taking the change in position over the change in time for the first few frames, and the video was about 24 frames per second. And then in terms of the fundamental physics principles, the computational model assumes a net force of 0, which is near impossible to pull off in a real experiment, which could cause the differences in the calculated and observed positions or velocities later down in the line. Additionally, this particular model demonstrates Newton's second law because it utilizes a momentum principle to update the velocity and position of the ball. You can see the two equations in GlowScript code at the bottom of the slide. The formulas are shown there, and you can see that the F net over the object's mass demonstrates Newton's second law. So based on these two models, we created an observed versus predicted graph. Here you can see there's a slight difference between the computational model and the experimental one. The computational model, which is in blue, stays linear and consistent throughout, whereas the observed one has more inconsistencies. This can be explained because the velocity of the computational model remains exactly the same throughout, whereas the velocity varies slightly with the observational model. This is most likely due to the fact that the observed model does have outside forces acting on the system, most notably friction, therefore making the net force not 0 and changing the velocity even slightly. And although these results seem conclusive, there still are potential sources of error. One such example is variation within tracker when plotting the object, or when we use GlowScript to create the values that were input into the graph, there could have been error there as well, human error. Another source of potential error is the initial push of the object not being centered or equal, resulting in less than close to constant velocity. Next up, we'll discuss some bigger picture ideas about this lab. So, what if? In this experiment, the right side was positive x, and the left side was negative x. And although the movement was in the negative x direction, which is to the left, if the signs of the velocity and positions would flip if the axes were interchanged. This would make the results graph have a positive slope. However, this would not cause a change in the result or conclusion we could gain from the graph. What does it mean? It's not reasonable to be able to say the exact amounts of the pushes and pulls. There are so many factors and outside forces that could be acting on the object. In the real-world experiment, it's nearly impossible to obtain true constant velocity due to the sheer amount of outside forces that could act on the system. In this example, like I said earlier, friction is a big issue that would slow the object down. So, in conclusion, the lab demonstrates the difference between computational models and observed models when dealing with movements of object with constant velocity in one direction. We can see that the observed model and experimental model differed from each other, since the experimental model did not have constant velocity, while the computational model had true zero net force. Thank you, and I hope you enjoyed.